this is going to be a whirlwind tour of all the forces. So it's not. I'm going to go. It's not a tour de force. It's a literal tour de force. And so we're going to go through everything, and we're going to try and do it as fast as we possibly can. So this will make sense in this way. But to really start, I want to say Yale is, I have a soft spot for Yale. I grew up not so far away from here. And basically, anytime I was on like spring break or vacation or anything, I used to come to Yale and not stay at home. And so I'd take the train over here and I would hang out in Pearson College, right? So all the time. And the reason I did was my best friend, growing up, like known him forever. He was in Pearson College. He's this guy. I don't know if you know who these two people are, but you probably know what they did. So this is the We Suck thing. And so this is, I guess I don't need to explain. Sorry, right. So, so the point is, like he actually called me up about 2 months before this happened. And he's like, you're at Caltech, you're doing all these fun pranks. He's like, we want to do something even better. He's like, here's a big plan. And like I had done a bunch of like little dinky pranks, like we tried to fix the Hollywood like walk-up star or something, a bunch of stupid things. But like he's telling me, and I'm like, it's never gonna happen. It's never gonna happen. And then like he like emailed me this whole like plans and diagrams. He made a little map, and like he's like, we're gonna do it. We're gonna do it. So yeah, he did it. And I encouraged him. I didn't think it was gonna happen. But there's all sorts of fun things. Like if you I know all these secrets about this plot, this site. Look carefully, Waldo's in there. There's a bunch of things in there, actually. So there's a bunch of hidden Easter eggs. But in any case, right, this is my friend now. He's a math professor. He actually doesn't live so far away from here. And here I am. This is from a year ago. Here's our friend Jeff. He works he does science funding in DC. So if you want funding. But anyway, just to point out, it's always nice to come back to Yale. But this story is going to start in Torino in 1845. So at that point, Charles Babbage and Ada Lovelace, who you might know as Lord Byron's daughter, turns out she is a fantastic mathematician, and she worked in Charles Babbage's lab. They decided to take a trip down from London to the Institute of Military Sciences to talk about the Charles Babbage's machine, right, the analytic engine, right? And at the time, they had this conception of how it worked, and they presented it, and one of the people in the audience, this guy here, this stately gentleman, he got very excited. And so he really spent another year trying to understand this. And so he wrote a kind of a big document in French about his understanding of Charles Babbage's machine, right? This is like the first computer. And so then after that, Ada Lovelace translated from French to English his document, and they made this document here. And out of this document came the concept of multiple instructions on a single processor. So what they realized is that this is the like analytic engine. You basically put all your numbers in, right? These are all your inputs. And in fact, there's like a lot of different rods, and you could actually put many inputs and many rods, and you could actually do something we call MIMD, or multiple instructions, right? And multiple data. And so the idea would be that you can send different elements of data to a different set of instruction set and compute them all at the same time. Now, this concept came out of this guy, Lorenzo Mambrea, trying to understand this analytic engine, and then Ada Lovelace translating it back into English, right? So there's a document where this idea kind of appeared. It's not clear who, in fact, did this. Could have been Ada, could have been Lorenzo, but some combination of the two came up with the thought that you could do multiple instructions. So, so what happened after? Well, they said the actual analytic engine never got built. Babbage had too many ideas. He kept tinkering. He kept saying it's going to work. And then at some point, the British government stopped funding this project. It fell through. Little counting machines became popular. You know, they in the 1850s, they put out a little counting machine that became super popular and people used up until the 1930s, actually, to kind of do computations. And incidentally, this guy became the prime minister of Italy in 1867. So, which is another interesting story. So point being is there was an idea to kind of parallelize computation, you know, more than 150 years ago. And this idea kind of reemerged at the Institute of Advanced Study in 1952. So there was a young engineer who just got his PhD, and he was trying to build a new computing engine for astronomers at the Institute. And at the time, they had this kind of memory device. It was this. This is the whole computer. Actually, sorry, this is the memory device. This is the whole computer, right? So just to put things in scale. And this memory device, right, it had like 8 outputs. And so the guy, and writing to the memory device turned out to be the bomb time. This is 19, yeah. And so at the time, like the engineer thought about this. He came up with the concept of, well, let's do multiple instructions and then just write these parallel threads, right? And this way we can at least mitigate the bomb. And so he actually brought up this whole MIMD architecture. And just to say, there's a related architecture called SIMD, which is different data sets, but then a single instruction set, as opposed to like, you know, 3 separate instructions for 3 different data sets, you know, multiply, divide. Well, this idea lived on, and people got excited. But at the same time, just down the street here on Route 1, at the New Englander Motor Hotel in Greenwich, Connecticut, a bunch of IBM executives were meeting. And actually led partly by this guy Amdahl, they came up with the concept of building a new computer. Right? This became the IBM 360. And what were the core ideas of this? The core ideas were trying to standardize the software so that things were backwards compatible, being able to kind of simply compute things, and you know, being able to make it easy for people to kind of switch between systems, right? So the upgrade system would work on the same thing. This led to the kind of assembly programming language that we use at the core of, like, you know, all software, and ultimately to, you know, higher level software languages built on top of that. Incidentally, if you try to go to the New England Motel now, doesn't exist. There is a Staples there. Yeah, I actually know that Staples. I've been there a few times. Yeah, so this became popular, and then out of this, IBM built the 360. This changed IBM forever. But at the same point, this got rid of this SIMD and MIMD architectures. People were just doing one computation, one instruction set with one piece of data at a time. And they were piping everything into that. And so these big machines that they made actually could only do one instruction set at a time. And there were kind of clever ways of maybe doing multiple, but ultimately you would just give it a vector and you'd take multiply, add, divide, whatever, and it would do it and then send it out and just do it very fast. And the whole machine would just, the whole machines were just designed to shuffle. And this was the standard for, you know, from 1962 when this was conceived, all the way up until IBM stopped making money, right, at around 2000, right? So, and you know, out of this came Intel, the CPU, the whole concept of the modern CPU emerged. But at the same time, in NASA, actually at Ames Lab in California, tried to make a parallel computer under this SIMD architecture by the same guy who had conceived this concept at the Institute of Advanced Study. And this became a huge effort. It became a huge money sink. The actual computer was called the Iliac 5, and ultimately was shut down. But it was able to kind of take multiple sets of data and do computations on the same time. And this is essentially what a modern GPU does now. So in the modern world, we have GPUs, they can do SIMD. We have FPGA, sorry, they can do MIMD, right? An FPGA is a chip where you can program all the kind of features of it. And ultimately, these started to win out once we realized that our ability to kind of power CPUs ended, right? So people always say, oh, Moore's law is dead. The real answer is something called Dennard scaling is dead, right? And Dennard scaling is our ability to put power in a CPU, right? So in fact, somewhere around 2010, our ability to actually put power on a CPU became limited. And so we went from going 1-core machines to 2-core to 100-core to like many core machines that you all probably use all day now for your CPU. And CPUs themselves stopped scaling in frequency, right? And this was a limitation of the amount of power you could put on the chip. Well, out of this came the rise of GPU architectures, FPGA architectures, all of these kind of multiple instruction, multiple data set concepts have kind of started to emerge, right? Once Dennard scaling hit it. And now, the world's completely changed. So the point being is that there was a time where there was this idea that we could do multiple computations at the same time. It's been around for 150 years, but we were kind of stuck in a certain paradigm where we're doing single compute, right? And the reason the single compute went out was because there was this idea from a big corporate idea to standardize things, make things easy to use, and it became the paradigm for how we understood computers. But ultimately, things got revived as we reached our technological limits, right? And so our environmental limitations sometimes force us to be smarter. And this is kind of the whole concept of this talk, is that we're maybe here in a new paradigm, AI is emerging, there's multiple instructions, SIMD, GPU architecture is emerging, and it's maybe time to think about how we approach physics, right, under this concepts. So I'm going to go through the journey of the forces. I'm going to go through all 5 forces here. And maybe talk a little bit about beyond. This is going to be a world war tour. It's not going to take 80 days. It hopefully will take, 55 minutes, but we'll find out. So I'll start with the electrowave force. And this starts at the LHC. And this starts kind of around now, maybe a little bit earlier, is that the LHC has kind of hit a midlife crisis, right? We've been taking data for a while now. We're kind of completely in the middle of our tenure, right? We're here in kind of run 3, which is right before we upgrade. And things are starting to kind of slow down and calm down. But I would say, in retrospect, we've done a very good job. Right? So here I have a plot of dark matter searches. And suffice it to say, right, all these colored bands are different exclusions for different searches of dark matter. And the point being is that we've been able to kind of exclude huge swaths of the phase space, right? Like basically, you can kind of definitively exclude a dark matter from a light mass all the way to high mass. This is under some assumptions. And so out of this, right, we, with these basic exclusions, people started to think about how we go forward. And one thing they realized, and this is a kind of when these exclusions started appearing, was that in principle, the way we produce dark matter in the early universe could be tweaked, right? So we knew kind of under the standard assumptions we made for dark matter that we had ruled out kind of dark matter. You would overproduce dark matter with the kind of model and couplings that we had. But we knew that by varying this coupling here, the dark matter mediator coupling and the dark matter to standard model coupling, we could evade this bound, right? And in particular, shrinking this coupling on the right, you could actually, allow for more parameter space. And so people started to make plots like this, where here you modify the mass of an intermediate mediator. So this is a mediator that couples dark matter and matter. And then you vary the coupling, and you find that there's a region kind of large coupling where you don't overproduce dark matter. But eventually, if you shrink the coupling so small, you end up actually freezing out so early in the universe, such a high temperature scale that there's just too much dark matter in the universe, and the universe would have collapsed and we'd all be dead, right? And so we have this kind of nice limit that drives us. And this kind of emerged out of going a little bit further from the kind of conventional paradigm of dark. So we had that, after we showed all these bounds, and we started to make new plots like this, where we scan the coupling, we scan the mass of our dark matter mediator, right? And then we make bounds, and we have limits. And so this is the most recent limit. And it's nice to see that, well, here's our kind of expected exclusion, like the dashed line. And so we've excluded kind of a region almost all the way down to this blue value, right? So the kind of all the allowed parameter space has been almost excluded by the most recent dark matter searches, right? And so the point being is that we've done a good, in fact, we've done even better job, right? We're kind of almost definitively excluding this for kind of a large set of models, right? So what can we do to kind of go beyond this? Well, the case I just showed you is an instance where dark matter is light. If dark matter is heavy, a mediator can't decay into dark. So it makes the search actually a little bit more difficult, or a little bit easier depending on the decay. And so in principle, you can have mediator decay to leptons and quarks, right? And so if the dark matter is heavy, the decays are still allowed, and we still want to get to this goal of the minimum coupling, right? So what do? Well, we search in this final state. The leptons are relatively easy. I won't talk about them. We have good bounds. But you can kind of pretty simply have models that just couple the quarks, right? And in fact, this is often the standard model that we use for kind of searching for dark matter. And there are kind of two ways to do this. Well, you can search for a light mediator, where you have a mediator that decays to quarks. To resolve this mediator, you make it boosted. And so you actually look for a mediator in a single jet. So you look for a shower of particles, and you look for 2 prons inside that jet. Alternatively, if you had a heavy mediator, right, you would look for 2 quarks, right? So you could have 2 jets. And then you do make a mess. It turns out, right, if you look at this coupling plot, that you need a large coupling to kind of not overproduce dark matter for a heavy mediator, and you need a small coupling for a light mediator, right? And it turns out the scaling of the coupling is actually linear with the mass, the mediator mass, roughly. And so, in fact, the heavy meters may be not so interesting, but the light is interesting. So we can search for it, and I'm going to show you a search where we do this. But we can also make our search a little more interesting by actually looking for different types of mediators. So if our mediator is to kind of all quarks, right, it would be kind of like a Z prime, so like a Z boson can universally to quarks. But sometimes the mediator could preferentially decay to heavy quarks, right? So mediator could go to B and P quarks, right? And that's kind of like a Higgs, right? Or a scalar, a new scalar. And these are all viable dark matter, right? So let's go ahead and do the search, right? This is a search. And we look for a jet, we look for a recoiling jet. In this case, we look for a jet that has 2 prons. So here's a shower of particles, resulted as a jet. And then you have a recoiling jet. The reason you need the recoiling jet is so that you can trigger these events, but also so you can reduce the background, because having 2 prongs nearby each other is a topology that's just rare to see at the others. All right, so that's the challenge. So we look for a resonance that decays to 2 quarks, could be 2 B quarks, could be 2 light quarks, and we want to reject it from background, right? And the background is just quarks and gluons, right? And the way we do this is we just take our jet, we look for this 2-jet topology, and then we just apply a normal. That's it. And so here's the search. I'll skip all the details. Here are our results. And so here's our light flavor result. And so you can see, right, you can look at the data Monte Carlo, there's no access, that's sad. But you can also see that you get this huge bump, right? And this is a W decaying to quarks. Actually, also a Z, so it's a merged peak of the 2. And this is a process actually we didn't think we could see at the LHC. If you go back to the founding of the LHC, nobody thought we could measure W to quarks. And if you actually integrate this plot, there's more W to quarks here than was ever produced at the lab, right? So this is actually the most amount of W to quarks. And here you can look at the heavy flavor, and now you can separate W's and C's, and you get a nice Z to BB bar peak, right? And so here you're actually seeing very cleanly Z to BB bar. This is a process that, they saw a little bit of the Tevatron, and I think that was it. Well, and at lab, right? They saw that, a lot of them. But suffice it to say, right now we're seeing it at the LHC, and we're seeing it with pretty good purity. In fact, the signal in the background here is greater than 1. So it's pretty spectacular. We can turn this into dark matter bounds, and it turns out, for certain models, I'll just take the right model. For dark photon, we've actually kind of translated this to an exclusion coupling. The red and blue lines here are Rayleigh density bounds, And you can see that our exclusions actually go beyond the relevancy. So we can kind of definitively rule out a dark photon that comes. Right? So this leads to kind of many interesting bounds. This green guy is our new result. This came out this summer. And the nice thing to see if you look at this, right? So this is the medium mass versus the coupling. That you see that like our results at the high mass have already kind of excluded the relic density. But our light results now are starting to push down and kind of definitively exclude dark matter for all heavy mediators, right? So this is a very strong statement, right? It's a big impact of this result. So we're kind of closing the path to dark matter. But what was the magic, right? I just showed you this peak, right? Nobody else can show you this peak. It's very hard to get here. And the magic actually was all in the deep learning, right? So this is the first version of the analysis in 2017. You can see a pretty small peak. And then we got a little more sophisticated in our modeling of the backgrounds. We were able to cut a little tighter. And this is our 2020 result. And then finally, we decided to add deep learning, right? And you can see the peak goes from this like kind of convincing peak, not so big, to this dramatically huge thing, right? And deep learning has really played a dramatic role on how we do this. And before I go into how the deep learning works, I'll show you kind of a little bit of how the next generation of deep learning will work. I also want to say that this heavy flavor result allows us to also look for the Higgs boson, because it turns out that high momentum Higgs bosons that decay to B quarks are actually living in this plot. And it turns out actually this single plot is actually the most sensitive plot to high energy Higgs bosons of any plot, because the Higgs predominantly decays to B quarks. And this is basically the most inclusive Higgs to BB bar, at high momentum that you can get. So we can zoom in on this region and actually study the Higgs. So how do we do this? Well, we're going to use a machine learning algorithm again, right? In this case, we're going to use a graph neural network. So machine learning algorithms at the LHC have evolved pretty rapidly as we've kind of gained the technology from industry. I won't go into the details of this, but suffice it to say, well, I'll say it for a second, right? We started with images, right? You probably remember like 2016, 2017, everybody was making convolutional neural networks, and they're all the rage, right? And suddenly, AI had, exceeded the ability of humans to identify images. So of course, people shoehorn this into LHC physics, but very quickly this got dismissed because, if I took this image and I boosted it, well, it would look completely different, right? Images are not Lorentz invariant. So then people got smarter. New AI algorithms came on the market. So these are AI algorithms that could take text and go word by word and translate, right? These are recursive neural networks. And so people were like, oh, words, text, same thing, right? And so people started fitting particles and secondary vertices into these recursive neural networks. And it got a little better. But these are really word by word. They didn't look at jets, right? They didn't look at the full set of correlations. The objects, right? And one word was correlated with its nearest neighbor word. So if I just ordered the particles to say by momentum, the highest momentum ones would be next to each other, when in reality, spatially, they could be completely different, right? So this had kind of limited correlations. It didn't work well. So then people started taking the particles and then connecting them. So you can imagine you put the particles on the grid, treat them as points, and now you make a fully connected graph where you connect all the nodes. So this turns out to work really well. And so this is actually kind of where the current collaboration results are coming. This is actually what made this, kind of enormous peak, right? And the transition from going from kind of these recursive neural networks to graphs was pretty dramatic. And recently, people have gone even further with transformers, right? And transformers are a fully connected graph, but instead of just kind of adding kind of the nearest neighbors and doing simple operations, you can now do things like attention, which kind of isolates the most interesting features, right? And so as each time you have these technologies, you kind of get better and better improvements. This is just to show you how much it improves. And we can then go ahead and apply this to the Higgs. And so why is the Higgs so important at high momentum? Well, it turns out like a large variety of new physics models will exhibit a very large deviation at high momentum, but they won't give a large deviation at low momentum, right? And so you can actually go for new physics in a completely new and unique way if you can get to high momentum Higgses. And the only way to do that is to go for Higgses with a high branch inversion, so Higgs to BB. So we do that, and we actually target the two top kind of production modes, boson fusion, vector boson fusion. We have a VH result coming out very soon. And this is our result, right? And so what we see is a very large excess, particularly in the vector boson fusion case. If you combine these two excesses, it's 4 standard deviations. The standard model expectation is 1.6, right? So it's almost 3 sigma deviation from the standard model. And this is a pretty enormous, like, right? So you see that here's your ZDB bar, there's your Higgs boson, and it's huge, right? And at the moment, we don't know what's going, right? Sorry. Sorry, I'm so sorry. That's fine. It was the right time to say that.
I'm so impressed.
But yeah, so we have this huge excess. And so we actually don't know. So that's the story's not over yet. But I do want to kind of bring in a little more insight about the machine learning and how we got this to work. Because I'm just kind of showing you these plots, and there's a lot under the hood. And rather than talk about these ones, I'm going to talk a little bit about the next generation of machine. So what we did in these plots was we had some kind of space, right, 4 vectors of particles. We fed them into a neural network, and then we output some discriminator, background and signal, right? What I want to show you is a new thing, often referred to as foundation models, where we actually make an intermediate space, right? And so we take a neural net, we give it a task, right? We build an intermediate space, and then finally we build like a little neural network on this intermediate space to actually do our discriminator. And so often people refer to this as like the first step is pre-training, and the second is a fine-tuning, right? So there's 2 trainings that go involved here. And what I want to focus on is how do I actually improve my neural network to model the data in Monte Carlo better? So I can tell you right now, all the neural networks we've done have been trying to train data in Monte Carlo, train data in simulation. Sorry, all the neural networks we've been working on so far, just train on simulation, right? And then we cross our fingers and hope that this works on our data and our simulation. And I'll show you that the simulation is definitely not, right, in a few plots. And so the idea was, what if we built an intermediate space where we projected away the knowledge between data and Monte Carlo that we didn't understand? And the way we did this is with contrastive learning. So this is a new paper from like a few months ago. And the idea here was to try to take 2 objects, say a cat and a dog, and then augment these objects. So give them some glasses, and then connect these in a space. So I want to say the cats are the same and the dogs are the same, but the dogs and the cats themselves are different. And so I built a neural network, and I gave the guiding rules of this, right? So align cats and align dogs. And so what it does is it builds a space where one side cats will live, and the other side the dogs will live, right? And the dogs, the cat and the augmented cat, right? They'll live close. The cat and like a different cat will live a little bit further away, right? And likewise the dog and the dog. And the way we do this actually is we write in our neural network a loss function, or we just take a cat, we augment it, and we require these to be close. And then we take a dog and augment it, we require that to be close. And then we say that all of the events, right, have to have a total distance, n, like an RMS of distance that's some number, right? So what does this do? Well, it pushes these things close, but it wants the distance between all of the data sets to say V1. And so what it will do is it will push all the other kind of objects farther away. Now, it turns out, right, if you just do this with cats and augmented cats, the other cats end up being nearby, right? Because the space starts to learn what cats and dogs are, right? And you're not telling it cats and dogs, you're saying cats and cats with sunglasses, right? Same image should be the same. But it naturally starts to learn that cats live in one spot, right? Dogs live in one spot, and starts to learn the concept of a cat and a dog, right? This is what contrastive learning does, is you try to maximize the separation between all of the objects in the space, right? But by virtue of maximizing that, you start to order the data. So this is you're giving it a little task, right? The neural network, and it's starting to order the space. And the nice thing is that if you give it the right task, you ask the right question, you can tell it to kind of order the space in a nice way. So the question we're gonna do, we're gonna take a Higgs, we're gonna take a QCD, and we're gonna actually split this by flavor. So we're gonna look at the kind of first decay. So Higgs will, in this case, is gonna decay to BB bar, and the QCD, for example, will have a blue to BB bar. And we're gonna augment our Higgses by our Monte Carlo uncertainties. So we'll take the Higgs and we say, well, we don't know how B quarks decay exactly, but we do have an ensemble of models that describe the B quark decays. And so we're going to take the Higgs and reshower the B quarks with all these different uncertainties. And we're going to say all of these should live in the same spot in space, right? And you can do the same thing for your quarks and gluons. You can take the same gluon, same matrix element, same exact pair of gluon to BB bar splitting, shower the B quarks many different times and say they should live in the same space. So that's what we're going to do. And this is going to be our pre-training, and then we're going to fine tune it out. So we took a Higgs, we modified the shower slightly, right, by our modeling uncertainties, and then we align them. And in fact, we do a bunch of different augmentations, right? We'll just take a Higgs and just reshower it. We'll take a Higgs and reshower it by modifying the strong coupling. And then we'll even take a Higgs and reshower it with a different showering model, right? So we can shower with Pythia as a baseline and Herwig as an augmented model. And then we project these down to 1 point, right? So we require all the Higgses to live at 1 point, all the quarks to glue to BB bar, right, to live in the same point. Same event, augmented event have to live in the same point, right? And so just to show you, this is what it looks like. Here's a red and blue. These are the same Higgs event, same matrix element, just different showering, right? There's a light quark, different showering. And we require these events to be projected the same. And this is the space we get. So it doesn't know what a Higgs is. It doesn't know what a quark is. It doesn't know what a gluon is. But if we take an 8-dimensional space and then this is projecting into 2, you see that the Higgses live in one spot, the quarks live in another spot, and the gluons live in another spot. And moreover, I can take my Higgs and vary all my uncertainties of my modeling, and they live in almost exactly the same point in space. Right? And just to show you, if you don't, I'll skip this slide. So what did we do? Well, let's just take an observable that's kind of like the observables that we built in our space. This is the N2 variable. This is actually the variable we used to use to find Higgs bosons before. And I varied, the C and the QCD scale and the shower model. I get these very large variations. So if you look at these bands, right, this is the size of the variation of the distribution. So you can see variations in the order of 50%, right, in some region. And you can see, what kind of very large variations just by changing the shower model. If I take the equivalent variable with the same discriminating power that I get from my learned space, I get this kind of variation, right? Nothing, right? So I can take the different shower model and I can get very good Higgs and quark discrimination, right? But I can see that this variable is completely insensitive to it. So I projected away my uncertainties, right? And so this is the kind of questions we're asking now, right? We're not just trying to train signal from background. We're trying to train signal from background in a way that mitigates all of the uncertainties so that we can actually get strong and powerful discrimination power when we go from simulation to data. All right, so now you can look at performances. You can make a bunch of ROC curves. And basically what we see is that we can actually preserve state-of-the-art performance, but reducing all the systematic uncertainties. And so in fact, this red guy here is our fine-tuned model. So we do a training and then we do a fine-tuning on the model. So the training reduces our uncertainty. And then the fine-tuning brings us back to full discrimination power. And it actually keeps the kind of uncertainties small, right? It doesn't really change the impact of the uncertainties. So this is our kind of fine result file, result. And we can compare this to kind of the conventional approach where we just do fully supervised. And you can see that we get the same performance on the same exact data set, right? So in fact, we did this systematically on the same data set. Now, the kind of fun thing is that we can do this training, and then we can go to other data sets and just try the performance. So so if we go to another data set, so instead of doing Higgs versus background, we can do a W boson decaying to quarks versus background. And if we took the same model that we trained on the Higgs, and then we just fine tune it on the W bosons, right, we actually get better background rejection than if we were to just take a model from scratch and train it on W bosons, right? We get another something like 15–20%. So what have we done? Well, we built a model that learned all the topologies of quarks and gluons and jets. We trained it on a lot of events, and then we were able to transfer this knowledge because we have this nice clean space, right? 8-dimensional space that captures all the physics we care about. And we can then just go to other domains, right? Other problems, and actually very quickly solve them. And so we're better than state of the art by kind of machine learning algorithms on the same data set because we've been able to capture this knowledge and transfer it, right? And so this is what people call foundation models. It's a model that you train on a large data set and you solve many problems at the same time. All right, so there are lots of things you can do downstream once you've built the space, right? You can imagine doing augmentations where you augment data on Monte Carlo simultaneously, right? So here's a paper that will be on the archive this week. And we get some performance improvements. And even if you don't, let's say your simulation data still disagree, you can then take this space, it's only 8 dimensions, right? And you can actually correct data Monte Carlo by using, by actually just mapping the distributions in the control region. So like we normally do, but here we have a nice approach where we use normalizing flows, and we actually map the quantiles perfectly. So the blue here is our background from one region, the red is a background from a signal region with different power models, right? And then if we do quantile morphing, we can fix the blue and the reds of the ground top region. This allows you to get kind of perfect data Monte Carlo agreement. So what did we do, right? We built a foundation model, but really what we did was we took a neural network. Well, we took what was in old times us coming up with some variables. Usually we asked a theorist to kind of come up with some variables that we thought were interesting. And then theorists will say, oh, here, these 8 variables will be great. And we build an 8-dimensional space. And then we're training like a BDT or a neural network to kind of run these variables and getting performance. We've never placed this theorist with a neural network, right? Where we just gave it a bunch of rules. Now, the reality is, right, the theorist is still there, right? And like, I went in and talked to that theorist when I was writing this paper, and he gave me lots of good advice on how to guide the neural network, right? And learn this correctly. But the reality is that, we don't need a theorist now computing these variables or coming up with variables. We can just go to machine. All right, so now I want to ask a question. All right, I just consulted theorists and QCD variables in particular. But I actually want to ask the question of, well, how do we dig deeper into QCD to make our machine learning, to make our simulation better, so that we don't have to kind of learn on the data or build these prescribed kind of learned variables in this space. And so, well, the question to ask yourself is, well, what is the strong? Well, we know how weak force decays, right? So, we have flavor changing decays for the weak force. This is a kind of classic beta decay. And we know how the weak force works, right? There's, this notion of flavor changing. You can understand that. We know how the electromagnetic force works, 1/r² potential. But if you ask somebody how the strong force works, well, it's a little bit confusing, right? You have a 1/r², right, at the end, and you have some confinement thing where the coupling is very large and it's the actual kind of R dependence is strange. And then you have a region where the coupling is kind of constant, right? And things just kind of uniformly distribute. Well, recently, Ian Molt, who's here, right, brought up this idea of bringing these energy correlators as a way for actually measuring the QCD potential, right? And you can kind of see this in this plot. This is the second order energy correlator. You can see that you can capture all of this, the 1/r², high transition to large coupling, and then the fact that the coupling is constant in a local region. You can see all of this in this plot. And out of this, its evolution, you can actually start to understand QCD. You can look at how this plot behaves with energy, gives you a notion of the strong coupling, but you can also dig deeper. And I want to show some plots where you actually dig deep. So this came from Ian. Here he is. I don't know. Does he still bike around Yale? You guys know this? He's like a BMX.
Hit his head.
Oh,
Yeah.
okay. There's a video of him doing tricks at MIT, right, when he's a student, right? Like jumping off like the stairs and stuff. But yeah, so there's Ian. So he came up with this idea. And the idea is pretty simple. You take a jet, you take your particles, so say you have 3 particles, and then you want to reduce this to kind of a single plot. You can compute the pairwise correlations, right? And so this gives you a notion of distance, and you energy weight your correlations, so you get a plot like this. The construction of the plot's a little confusing because it's not, particles are correlated, but each of those bins are correlated with each other. So understanding the statistics is a little bit annoying, but it's not something we don't know how to do. And this allows us to dig deeper because we start to capture the features, right? So we see if I just look at the 2-point correlator, you can probe, a gluon and a quark and how they interact. And you can see, right, the region here where you have constant coupling, right, at low delta R, the region where you kind of transition to 1 over R squared, and then the region on the right where you get to that 1 over R squared. But then you can start to look at more interesting things. But what if I have a B quark, right? A B quark will have a so-called dead cone. So when a B quark decays, right, there'll be no radiation around the B, and this is just because of the B quark is massive. And you can start to see features like this. So here we have the second order. By the way, you shouldn't. These are not public yet, so I probably shouldn't share this, but it's okay. They're not too dangerous. So the point being is when a B quark decays, right, there's no radiation around it because of its massive, and this just comes out of relativity. And so we can actually see this effect, right? So here, the orange guy, right, compared to the blue. So the blue is just a light quark, right? And the orange guy is a B quark. And what you see is this giant hump, right? And so what is this hump? This is actually a suppression of radiation at small delta R and an enhancement of radiation coming from the fact that there's a suppression. So it's pushing the radiation out, right? This is exactly the dead hump. And so you can see these kind of interesting features of QCD, things that have only recently we've been able to see, right? So Alice recently came out with the result, I guess about a year ago. You can then start to look at event topologies, right? So here you have a plot in E plus E minus, where you not only look at 1 jet, you look at 2 jet, and you can look at the QCD in between, right? So this region in between is where a jet would have been radiated. Here along the ends, you see that it's constant. And this is the notion that the strong coupling here is constant. So the fact that it's constant here, and you can see this transition. And you can see it's very well modeled. Right? So what if we go higher order? Well, and we start to take the 3rd order, right? Now you start to probe the case where you have a quark, radiates off a gluon, and the gluon decays. And you can actually compare this to the sec 2-point, and you have an additional strong coupling. You can take the ratio of these, and you can start to be sensitive to the strong coupling. So just by taking the ratio of these, taking kind of the slope of this correlator, right, you can actually measure the strong coupling. And here you see the strong coupling evolution as a function of momentum, right? And so you can actually see how the strong coupling varies with energy. And so now you start to see even deeper things, right? So this starts to give you some even more insight. But now I want to bring it to the 4-point correlator, right? And so what happens in a 4-point? Well, imagine you have a gluon, it splits to 2 gluons, and these gluons are polarized, right? Well, now you have a dipole and another dipole, and we can start looking at these configuration of 4 points and how they interact. So, and the problem is right now, once you go beyond 2 points, right, you have here, you just have an angle and an energy, right? 3-point, you start to have lots of angles and energy, and 4-point, it becomes a little ridiculous, right? So there's 4 choose 2 pair combinations, right? The energies of these are all different. So what we have to do is we have to pick specific configurations here in histogram. So we take a configuration. So we take a configuration like this of a dipole, where we look in our jet for quarks, or sorry, particles, proxies or quarks, right? Where they're configured like this, right? One is along this line and one is along this line. And then we have kind of 3 variables, right? The radius, the big radius of the 2 particles, a little radius, and then an angle across. And so we look for explicitly these topologies. And the way to think about this is that one is a gluon dipole, the other is a gluon dipole, and we're basically doing a product, right, of a dipole interacting with the dipole. And as you rotate this guy, you see that, well, once they're aligned, right, the dipoles are aligned, you suddenly get strong dipole-dipole interaction, right? And if you rotate them away, you suddenly don't see a dipole. So you're really literally seeing the dipole, a QCD dipole. And like electromagnetics, it kind of behaves like a QCD dipole, right? This is the full 2D plot as you rotate this guy. So you can really think about it like this. This is the 1D projection at the angle. Okay, well, let me show you something even crazier where we can take a T configuration. Right? So imagine your one particle is locked here, the other particle is here, and you have a T, and now you rotate this guy around, right? And if you do this, you start to see this plot here. So I don't know if you know what this plot, this is, by the way, this is LHC data, so I probably should show you this, but yeah, this is data, and you start to see this signature. Now, this is just cosine 2π, and this is a plot you might have actually seen before if you were in high school and you played with, you did like a physics lab on polarized light. You could take a polarized beam, polarize it one way, take another filter and rotate this filter. And actually, I found this on and rotate this on a filter. And you can ask yourself, well, what's going to be the interference of this? Well, this is just going to give you fixed light. And now you're doing a product of the filter with the other filter. So you end up with an intensity that's cosine squared. And you also have that when the filters are perfectly vertically aligned, you have full intensity, right? So when it's vertically aligned like this, vertically aligned like this, you have full intensity. And then when it's perpendicular, you have 0. So you end up with exactly cosine 2π. Right. So for 2 theta, right? The angle is theta. Incidentally, I found this diagram on an exam, like a college physics exam website, right? So and this is a multiple choice, the answer was B, right? So, but the point being is that what we're literally seeing here by doing this configuration is literally a test of the polarization of the gluon. So this is the first plot I've ever seen. It shows you kind of straight up that the gluon is a spin 1 polarized. And here's also the calculation from our theorist friend, Kyle. We think he just cheated and plotted cosine 2 theta. But the kind of fun thing is that this is actually where simulation breaks down. Right? So on the top here is Pythia, and the bottom here is theta. The different colors, by the way, are the little radius, right? So the purple is when the little r is the same size as big R, right? And so that's when you actually see the full polarized, effect. When those r's are small, you see nothing, right? You just see perfectly uniform distribution. If you look at Pythia, you don't see that, right? You see some weird effect. And then, as it gets larger, you see some enhancement, but it doesn't get super enhanced, right? Like the actual data. And so the data is what I would expect a spin 1 filter to look like, right? Just by playing with, polarization filters, with my sunglasses and so on. But the top is what actually Pythia is telling us, which is clearly wrong. And this is what people are training their neural networks, right? This kind of stuff and getting huge improvements, right? So I don't think the story is over, and I think there's a lot of interest. We can project away these effects, right? With fancy machine learning techniques, but we can't actually fix these until we actually understand the data deeper. All right, we're getting close to measurement. I showed you a bunch of stuff I published, but I figured I'm at Yale and you guys would like this. I will say that, we spent the past year coming up with a very clever strategy to unfold all of this and produce this result. The result should be out soon, right? But I won't guarantee it. Now, what is the impact of this? Well, it helps us understand QCD. It helps us prove our machine learning. But this is also a super powerful tool for the heavy ion medium. And this is something I am a big fan of. So I remember a few years ago, I did a project with Marta Verwey, where we measured the splitting function, right, of jets. And this paper has had a huge impact, right? Trying to understand how we can use jet substructure to understand the medium. And I think this goes one step further, because now you start to really see the problems. All right, I'm running low on time. So I'll skip this I'm just going to say that we're building a dark matter detector. And if you want to join, it's called SpinQuest. or darkquest, let me ask me. And then I can give you a choice. Do you want to learn about LIGO? Or do you want to learn about anomaly detection, or do you want to do fast machine? The three options.
Fast machine.
Fast machine learning?
Fast machine.
So suffice it to say, we're doing stuff in LIGO, and it works. We did some anomaly searches. All right, so how do we take data at the others? Right, we have a trigger, and we try to trigger events. Now the data comes in at 40 megahertz. We can't save all those collections. We're talking about hundreds of exabytes of data per year. And the way we think about the data is that, well, the lowest energy kind of crappy collisions tend to be the worst, and the highest energy interest tends to be the most interesting. So, as a function of energy, our data rate rapidly goes down, and we try to save the most interesting events, right? So we try to save the events that are, let's say, high energy. And we do this in kind of three tiers. We have a fast tier where we look at all the events. We decide if it's a high energy event that's interesting. We have an intermediate tier that actually looks in a little more detail to really decide if it's interesting. And then finally, we have a slow tier, the offline tier, where we actually look at it. Now, the thing is, our tiers are not very good, and we know there's interest in physics hiding. And here's just an example. This is a boosted Higgs boson. It just passed our cut. 450 was the cut, right? And had been slightly worsely reconstructed, we would have lost this event, right? So it's plenty of nice things. So how do we program these things? Well, it turns out the data rate is so high that we have to use special processing, right? And so we use FPGAs. Now, the way you think of an FPGA is think of it as a giant orchestra, right? The chip, you can imagine the chip is your orchestra, and every little part of the chip is a different player. And you can tell this player to play this note, you tell this player to play another note. This is the MIMD paradigm. And that's the way to think of programming an FPGA. You're trying to program them all at the same time. A way of thinking of a GPU is like a jazz band, right? Where they're all playing together. The drummer is probably the most important, right? So you're kind of just feeding in data at the same rate to the machine, and they all kind of play basically the same thing all together, right? And they can, maybe there's a soloist, but that's the CPU that's kind of connected to the GPU. The rest of them are just playing a rhythm section. So that's kind of how a GPU works. It's just single instruction, right? Multiple data, right? Multiple musicians. And then a CPU is just a soloist, right? But the CPU is powerful. It can be a great soloist, right? Any jazz musician would know this is McCoy Tyner, who's maybe the greatest pianist of all time. And I saw him in concert once. He's like, let's just say he refused to play with the rest of his band for the first hour of the time. Like they just sat there on the side and he just was playing, right? It's one of the greatest concerts I've ever went to. In any case, what I will say is that we have to use FPGAs, and the FPGAs have gotten very powerful. And I'll take a 3-year story and reduce it to one plot, is that when I started working on Trigger, I wanted to implement particle flow and puppy for the LHC upgrade. We had tracking, or the potential of tracking, and we had the potential of clustering and so on. And over a period of 3 years, we were able to take raw inputs that we got from our upstream trigger systems and write a full particle flow and puppy algorithm that can take a collision like this and reduce it to a collision like this, right? These are the same events. This is the same event, right? And what we've done here is we've gotten rid of all the overlapping pileup. We've gotten rid of all the deposits and merged them into particles. And now we can actually interpret this event by hour. Like here, it's almost impossible. Here I can look at this and I actually see, something like 6 jets, right? And I can tell you this is an all hadronic TT file. So suffice it to say, we learned a lot. FPGAs became very powerful, and we've been able to do a lot of kind of incredible things. So we already have this algorithm. It's ready to go. We're just waiting for the LHC to upgrade its beam, and then we'll start using particle flow and puppy in our FPGA level 1 tree. But after we did this, we asked ourselves the question, well, how could we go a little bit further? This is 2018, 2019. Machine learning was just starting to become popular. And so we asked ourselves the question, how could we put a neural network onto an FPGA and run it in the time constraints that we have at the LHC? To run this on all 40 megahertz collisions, you needed to do this in less than 1 microsecond, right? And so what we did was we had to rethink how we did machine learning on a chip. And it turns out nobody had really thought about this, at least for the last 30, if not ever, years, to really think about how you put AI that can run this fast, right? And so we ended up building a new paradigm, right? This is not something that we had seen in industry at all. And the only reason we did this was because we had this 1 microsecond constraint to make our neural. So what did we do? Well, here's a simple neural net. I've got 2 inputs and output. And what do? I take my 2 inputs, I multiply it by 2 weights, right? I add a scalar, and then I apply an activation function, and then I output. And so this is the way I would write my neural net, right? Just, on paper, with math. The way I would do this in kind of iterative scheme is like this. I have 2 inputs. I first run my multiplication, right? I do my multiplication in parallel. Then I add the 2, right, together. And then I apply my activation. Now, the way I would do this on a chip is I think about this in terms of a clock, right? We've got a beat, right? So in the first clock, I do my multiplication. The second clock, I do my addition. And then my last clock, I actually apply my activation. And the way we do this on an FPGA is, well, you have multiplying units of DSPs, right? Addition you can do with flip-flops and some lookup tables. And then the activation is just another lookup table. It's just a function. We know how the function behaves. We just make a lookup table. And so you can take a neural net and in 3 clocks on a chip, right, run the full inference, right? 3 clocks. These chips are typically running at 2 nanoseconds per clock. You're talking about a neural network that can run in 6 nanoseconds, right? That's about I think that is the fastest neural network in the world. Now, granted, you're limited by the number of multiply units. You're limited by the ability to add these numbers, right, in a single clock, and you're limited by the lookup table. But it turns out you can do a lot even with this. Right? How does this look like on a chip? Well, this green guy is actually a neural net. Right? So this is one of our boards. Right? This is one of the boards, and we have a bunch of different algorithms here. Most of this is just data flow, right? Processing the data in and out. And then this is a neural net that goes on the chip. What is this neural net? Well, it turns out this neural net is actually doing p-tacking at level 1. This is something we will be able to do in the upgrade. And this allows us to actually kind of dramatically improve our sensitivity to kind of new physics. And in particular, we benchmark this on the Higgs, the Higgs self-coupling measurement. So this is looking for 4 Bs in a single trigger. And we look in the low Higgs mass region, right? This is where you're sensitive to the Higgs self-coupling. And you can see that, from the 4-jet trigger, which is what we had before, you can actually kind of more than double, right, your mass, right, by adding this p-tagging. And if you add a soft muon trigger on top, you can kind of improve things even further. And so we get there are muon triggers in 4 jets before. So we were kind of at this light blue line. So we get something like a 30 to 40% improvement. And this probably gets all the way to the measurement of the Higgs self-coupling. And this network, right, runs in 80 nanoseconds. So this is one of the fastest networks in the world. It's not a large network, but it dramatically improved things, right? And so now we can think about things like we saw offline, where we have taken analysis, we just run a neural net and we move on, right? It's like a building block, right? It's now codified, right? And in light of that, we made a tool, HLS/ML, that allows us to just do this automatically. Right? So we can take a neural network, we install the tool, push a button, and then it overlays the algorithm onto the chip. And this paradigm of kind of, fitting the neural net onto the chip, unrolling it like this, was a new paradigm. People did not think about designing neural networks this way, right? And you can actually look at this chip carefully, and you'll see that one region will be layer 1 of the neural network, one region will be layer 2, layer 3, and so on. Traditionally, the way people coded these networks was they had a big matrix multiply, and then you were shuffling data in and out, right? That's how all the other people design neural networks. This is how GPU works, right? This is how other FPGA implementations. So it turns out by doing this thing like as fast as possible, we built a new pipeline that shoved the neural network through the data. So this is a new way of ML, right? And so we made the software tool, and now people are starting to realize it's very powerful and you can do many things. We were able to scale the software tool to do not just small neural networks, but many, like very large. So my personal record is I got resonant 50, so this is a 50 million weight neural network. I spread it across 20 FPGAs, right? And so I interconnected them. But the idea here was that different layers of the neural network. This is a 180 layer neural network. We spread them across and all the different FPGAs. And then with this, we were able to run the fastest neural network, single inference neural network for resonant 50 in the world. So there's lots of new applications that came out of this, and many exciting things. So one thing you could do is cell therapy. So you can imagine cells going through your blood, and you make a little optical CNN neural network that identifies your cell, and if it's cancerous, you tag it, right? You have 20 microseconds to do this in your blood. The tools exist to do this, but you needed a neural network that could run this fast, right? And so in fact, we're doing kind of a pet project now where we try to cure cancer by tagging cells, right? And then, what you can do is you tag the cell and then you take a pill and it kills the cancer, right? So if there's cancer in your blood, you can tag it this way. So that's one thing that we're thinking about. Another is actually quantum computing. It turns out by making networks under this paradigm, you not only make them faster, you dramatically reduce the power, right? So you end up with very low power neural networks. And so you can take your chip and put it in liquid helium and actually read out quantum computers and denoise them. So we have some projects now where you're denoising quantum computers, right? Because you can put these FPGAs into liquid helium and they work without boiling helium. There's now applications to do this on your phone, right? The neural networks, because they're low power and they're very efficient, there are now people talking about using the same ideas on your Google Pix camera, right, and actually doing image recognition, right, using the HLS from neural paradigm. And actually another project that we're working on actually very actively, this might be a real reality very soon, is that we're looking at taking brain sensors and actually translating them to physical motion. And in fact, we already have kind of models that we're developing. We have some monkeys and rats that we're going to test this out on pretty soon. So this is doing real-time brain controls, and the kind of timescales you're talking about here are like tens of microseconds. So let me end this talk with kind of a parallel to the original beginning of the talk, is that we're not the first people to do this, right? So in Fermilab in 1989, a guy by the name of Bruce Denby wrote a paper on neural networks for triggering, and he was trying to put this on some hardware. FPGAs didn't really exist. They were kind of custom chips they would make at the time for different projects. And this kind of, people got excited by this, but it kind of fizzled out because people didn't know how to program the chips. There wasn't a standard paradigm for doing this, and machine learning was in its infancy, right? So it never panned out really due to the limitations of computing. But now we have this new standard where people are starting to think about machine learning, right, for everything. And also we have a nice software tool where we can standardize this work, right? So like IBM did with the 360. And so now we're building a group, we call this the Fast Machine Learning Group. One of the big sub-institutes is an institute called A3D3, which I'm a deputy director of. And the idea here is about bringing fast machine learning to all the different science domains. So we have examples of neutrinos, gravitational waves, LHC physics, neuroscience, and more. And there's recently the CERN NextGen project, which was kind of built on these ideas to build a next generation trigger. So in fact, exploit HLS from now and exploit some of the stuff we've done, machine learning and GPUs to kind of trigger every single event. And there's also the Fast Machine Learning Group, right, where I encourage you to come to our workshop next week. So Fast Machine Learning is like the superstructure of all these other institutes. So if I were to build a vision of where we are, is that AI is starting to really come in and actually be a very powerful tool at the physics analysis level, right? We can do analyses that we just couldn't do before, right? And we can do things like important ones like bounds on dark matter, high momentum fixes. A big component of this has been being able to understand the compute, like being able to make the algorithms larger, being able to make them faster. But if you go to the core elements and you drill down, how do I improve my physics? Ultimately, in the end, it's about understanding how well we can model the physics how we can build our simulation. And so, if we can get all of these things in together, you can imagine a world where a lot of kind of new physics and physics understanding becomes automated. And so you can imagine looking at data sets and automatically understanding the regions where we model things well, automatically looking for new physics. And this allows us to kind of go further and deeper in the data we never had. So on that, there's lots of new things we're preparing for the future and thank you. So.
So we can open up for questions.
So when you were talking about the machine learning with augmentation, you were saying that reduces the dependency on the uncertainties, systematic uncertainties. How do you know that also reduces the dependency on data Monte Carlo disagreements?
All right, so we don't per se, but what we do know is that the data and the uncertainties that we span, data Monte Carlo live in between. Right? So you can know that if we vary this uncertainty up and this uncertainty down, and we go to do all these studies, that the data lies in between. And so the thought is by doing all the variations that cover the data in many different regions, we can kind of compress them, contract them all into a single point, right? And so by construction, they end up being in the center. And we've done test studies where you apply run this on Pythia, apply it on Hardware and things like that. But we haven't done this on data, right? At least not. Yeah.
So I have one question. I have a bunch, but we'll focus on an overarching thing, I think. So I don't work on machine learning. I'll preface by that. But you say that using machine learning for triggers will allow us to understand, to get more into the physics that we don't know. I would think that if you're training it on data and stuff that we do know, wouldn't it bias you towards what you do know?
Yeah, so that's a very good point. So let me rephrase your question slightly, is that if you train data on simulation, right, you're kind of limited to the scope of knowledge.
Right.
So how do you go beyond that? Right. So that was a whole section of the talk I skipped. But the reality is that you want to build a space. And so there's all these kind of new ideas. So I showed you a space where we did these augmentations, we built a space, right? That space, if you do it cleverly, can actually interpolate around new physics. So we have another example where we build a space and we kind of train it with a hypothetical signal and background, but we know that other true signals are there. And it turns out we can be sensitive to all of these effects in space by a clever construction of this.
So then, okay, all right. Then I have another one. So usually, the way that my understanding at least is, say you wanna study the method behind, I don't know, fragmentation in jets.
Yeah.
You take Hardware, you take Pythia, you turn something on in Pythia, turn it off, go to Hardware, turn it on, turn it off, and then you start juggling all these. Is that something that you also can do? I'm assuming.
That's right.
Okay.
That's right. So this is stuff you can do in a simulation. And so my point being is that we can turn them on and off and then train them all together.
I see. Okay.
And it's about giving the rules to the neural network to do what you want. I showed an example where we just try to project them away.
Right.
But
Yeah.
there are other examples I have in the backup where we actually turn them on.
I see. Okay, I have one more, sorry.
Yeah.
And then unless someone else has another question, in which case I can ask it, but I have one. Okay, so then you say, okay, we have a model, right? Say we have stuff like Gen4, we have Pythia, we have Hardware.
Yeah.
But then when you go from, I've always struggled with this, where it's like you take the model and then you tune it to whatever your experiment needs, right?
Yeah.
Whether or not that's physics or there's something weird with your detector, we don't really know. With something like this, do you think, but then like, for example, we take Heron data.
Yeah.
Then we take what we think we understand from Hera. We look at a similar observable in LHC, then we look at a similar observable in Rig, and then they all have different.
That's right,
And then how do you end up making a story? Because in my head, I'm like, the physics should be the same
that's right.
question. And then what, I'm like, you see what I'm saying? Do you think this is something?
Yeah, so, I mean, yeah, this is a very important story, right? So, it depends on the question you want to ask. And so if you're trying to look for new physics,
Yeah.
right, you want to control your background, you can kind of, take your backgrounds, this model one, tune them, and then they look good, and hopefully your signal is
Right.
not moved, right? But the reality is that doesn't really solve the problem of getting blue and red to kind of agree.
Yeah,
The real approach there is you want to maximize. So you want to, let's say I want to study the differences between blue. Like the strategy there is to then, actually go, run all the video with all these parameters, run Harwick, run your different tune models, right? And then scan them all, right? And I mean, ultimately in the end, the AI will allow you to do this
Yeah.
higher dimension. But in the end, the physics is the part that wins out. Like
Right.
I don't have a solution for that, right? But I have a way to kind of speed up the process.
Yeah,
of
yeah.
learning. So things you can imagine doing, where is you can actually, these spaces are just kind of learned spaces,
Mhm.
but you can actually require these spaces to have specific properties, right? And so then what you can do is you can kind of emphasize, let's say one of these axes, I want it to be correlated with spin, right? The spin of, and I make these simulations, right? And I actually say, when I embed my space, axis A has to have the spin effects in one region and like it has to reflect that, right? And those are guiding tools you can use in the machine learning. So you can tell the reason machine learning is like, make one axis focused on spin, make one axis focused on this. And these are things that you can emphasize, right? And like, this is stuff that people often don't talk about is that there's all these intermediate like layers where you can ask all these scientific questions. The hard part is the science part. The machine learning is just a tool. We can sit and chat for like 10 minutes and I can show you, how to write a loss function and, and then, fine, you ask somebody who knows how to do this. It's a learned skill. It gets easier every day to do these things, so.
Just like a very, very small follow-up question on this, because I guess Yves mentioned, using this on Hera data, and then you somewhat flash through LF results that I guess.
Yeah.
So here, my question is like, I really like the structure of the talk going forward for, higher data streaming and see the obvious application to using newer techniques for that,
Yeah.
especially for the triggering aspect. But I guess from your experience now, going back and digging up archived data and applying newer techniques that weren't present back in the day, because this seems to be, in my group of friends, the vogue thing to do now. You go to an experiment that doesn't exist anymore, get the pen drive where all the data is, and then apply your model, and then you got different results than were available back then. So what sort of lesson has been learned from this? And then also, what are the potential sort of like, let's call them dangers of looking back at data that's already been analyzed, and then because we don't want people to roll in their graves about us writing different results than what they presented back in the day, right?
Sorry. Okay, yeah, so all right, I'm gonna give you a long answer. This is a good question.
We can also chat about it offline, but this is something that I was just
Let me give you like a
Yeah.
3-4 minute answer. So the point is that when we do analysis at the moment, right, we often just take the final state particles and then we look at it, and then now we're like, oh, we have machine learning. Let's do neural nets. Let's train A versus B, right? Let's train some regression to correct the energies, right? You do something. The current in vogue thing amongst the people who like machine learning is to kind of propagate this downstream. And the new thing that you probably have heard about are people who are taking old data sets and let's just rerun those reconstructions. Right? Now, I'm going to give you a very biased view, is that we've done this, right? At least with LHC data. And yeah, you can get some improvements, but they're not large. This is the one case where we went from raw to energy reconstruction. It's the only one where I saw a significant improvement. It's like 10%, right? And this is a huge amount of building a neural network, very complicated neural network. We tried this even with clustering, and you got basically the same as clusters, right? We couldn't get it better. The reason we did this was that it was much faster, right? This is like 1,000 times faster than clustering, right? So for fast, like, it makes a lot of sense. The actual kind of core physics, right, that we're learning from these algorithms is no better than what physicists have been doing for 50 years, or tuning these algorithms, making them really good. You know, there's a lot of discussion, oh, machine learning is going to take over track reconstruction. Track reconstruction is very good, right? We're really good at it, right? If I were to put money on it, I don't think it will ever. I think they'll have the same performance, but I don't think it will beat the machine learning tracking one. I mean, it might beat it in some corners of phase space, but it's not going to be a like huge paradigm. So like putting an ML and then just reanalyzing, kind of like to do reconstruction, I question whether they're gains. The gains that we have seen, right, are things where like processes we just didn't think about. Right? Like, you know, when we were trying to do this, like we saw these huge gains for this boosted W, right? So these high peaking W peak, right? We saw huge gains from machine learning, but that was partly because people had just not seriously thought about this problem. There's this jet substructure emerged as an idea 15 years ago. The first kind of 5 to 10 years was convincing ourselves that we could do this, right? And only recently people are like, oh, let's just shove every single bit of information into like a neural net or something that can process all this, right? And only now have people gotten the confidence to do this. The part I don't talk about in my talk is that there's like 2 years of blood, sweat, and tears to get this data on color, right? And there's a lot of things under the hood, right, that are hidden here, and it's just as hard, if not harder, than doing a normal analysis. So, you know, the point is, it was worth it here because we had a huge amount of background. Now, if you want to go to lab, you want to do analysis, right? There's no background, right? You know, you select the events. Now, you know, if you have some fundamental variables, like Ian has his variables with this nice features of QCD, and you can reinterpret things and learn something, that's useful, right? But if you want to go back and reanalyze just because you have neural networks now, I would seriously question it unless you have a real legitimate case for like removing background, removing things that you don't necessarily care about. The machine learning is good at kind of highlighting the features, and, you know, but it's not like a you know, clairvoyant solution that will, you know, by reanalyzing data, we're just going to suddenly learn all this new physics.
Right.